Hello and welcome to Exploring the Cosmos from the South Pole Ice, a virtual tour through the IceCube Neutrino Observatory. My name is Jocelyn Argueta and I will be your first virtual tour guide for today's journey through the coolest astroparticle physics experiment on Earth. I am a science educator based in Los Angeles that uses the performing arts to communicate science, most recently through my live show for kids, Jargi the Science Girl. I first heard about IceCube when I was selected as a polar trek educator to travel to the South Pole and help bring this amazing research to a broader audience, in English y en español. Now you may be feeling a little bit like I did at the start of this adventure and wondering, first and foremost, what is IceCube? The IceCube Neutrino Observatory is probably the strangest telescope in the world. When I first read about it, I could barely believe that such an ambitious project was being successfully executed in one of the harshest climates. The project is maintained by the IceCube Collaboration, which is made up of 400 physicists, computer scientists, and engineers from 53 institutions in 12 different countries. The University of Wisconsin-Madison is the lead institution and headquarters of IceCube's maintenance and operations. The observatory itself is made up of 5,160 basketball-sized optical sensors, called digital optical modules, or DOMs for short. These are attached to 86 vertical cables, called strings, and are embedded in a cubic kilometer of ice at the South Pole. IceCube looks for signals from mysterious particles called neutrinos. These are chargeless, nearly massless, fundamental particles that travel close to the speed of light. They are the second most abundant particle in the universe, outnumbered only by photons. In fact, about 100 trillion neutrinos pass harmlessly through your body every second. But where do they come from? The Big Bang, the sun, nuclear reactors, particle accelerators, Earth's core, your bones, even bananas are some of the sources we know of. But IceCube is interested in astrophysical neutrinos, which are produced in some of the most violent and least understood events in the universe. Events like supernovas or neutron star mergers, and objects like active galactic nuclei or black holes are just a few possible sources of high-energy astrophysical neutrinos. Neutrinos are often referred to as ghost particles because they only interact through two of the four known forces, the weak force and gravity. That means that they can travel for billions of light years on perfectly straight trajectories, unperturbed by magnetic fields or intervening matter like interstellar gas, dust, or even stars. So if we see a neutrino on Earth and can determine its trajectory, we can trace a straight path all the way back to its origin, perhaps millions or billions of light years away. This makes neutrinos valuable cosmic messengers, allowing us to probe distant astrophysical events. Of course, the fact that neutrinos so rarely interact makes them extremely hard to detect. So how does IceCube do it? The higher a neutrino's energy, the more likely it is to interact with matter. Fortunately, IceCube is looking for very high-energy astrophysical neutrinos. When a neutrino gets close enough to an atomic nucleus, the weak force comes into play and an interaction happens. The neutrino basically bumps into the nucleus and produces a high-energy charged particle, like a muon or a tau. In the ice surrounding IceCube, this charged particle travels faster than the speed of light, since light is slower in the ice than it is in a vacuum, and produces a cone of radiation, like a sonic boom for light. This Cherenkov light triggers IceCube's in-ice DOMs, and when multiple DOMs are triggered in a short period, it becomes known as an event. Each DOM houses an extremely sensitive photomultiplier tube and mini-computers that relay data to the IceCube laboratory at the surface. IceCube collects a terabyte of data every day, predominantly signals from cosmic rays and neutrinos produced in the Earth's atmosphere. The most interesting data, about 10%, gets sent daily via satellite to our scientists all over the world for analysis. The very high-energy astrophysical neutrinos that we want to see are rare. IceCube detects only a few dozen of these a year, but they are well worth the wait. In 2017, IceCube had one of its biggest discoveries yet. We detected a neutrino coming from a blazar more than 5 billion light-years away. Shortly afterward, the Fermi and MAGIC telescopes saw a gamma-ray flare in the same spot on the sky. This blazar is the first known source of high-energy astrophysical neutrinos, and it resolved a century-old mystery. Where are the high-energy cosmic rays being produced? This detection is also an early example of multi-messenger astronomy, where researchers combined measurements from different particle messengers to get a more complete picture of our universe. It's an emerging and fast-moving field of study, and neutrino detectors, like IceCube, are essential to propel this exciting new research forward. But that's not all that neutrinos are good for. In fact, these particles are so versatile, they can help us resolve a number of the universe's riddles, from dark matter to maybe even the reason matter exists at all. Yes, we can learn about all of this thanks to data collected by a detector frozen in ice at the bottom of the world. Which brings us to another frequently asked question: why build IceCube at the South Pole? Well, in order to detect the Cherenkov light given off by charged particles produced by neutrino interactions, you need a large quantity of transparent material, so water or ice, and a lot of it. The South Pole has such large quantities of pure, clear, stable ice, and it has the infrastructure to support science. Since November 1956, the National Science Foundation has hosted Antarctic researchers at the Amundsen Scott South Pole Station, but you'll hear more about the station later. Most ice contains bubbles that would distort IceCube's measurements, but the South Pole ice sheet is very thick, almost 3 kilometers. As snow and ice piled up over time, the lower layers of ice were compressed. This immense pressure forced out air bubbles and made the deep ice ultra-transparent. In addition, IceCube needed to be shielded from the background of muons produced by the Earth's atmosphere that can look deceptively like neutrinos in the detector. We were able to take advantage of the South Pole ice for that. IceCube's DOMs are buried in the ice beginning at a depth of about 1,500 meters below the surface, greatly reducing the number of atmospheric muons reaching the array. It took 7 years of work, from 2004 to 2011, to complete the construction of IceCube. Construction activities could only take place for a few months each year during the Southern Hemisphere's summer, roughly November to February. Construction required drilling holes 2.5 kilometers deep into the ice with a custom-designed hot water drill. It took on average 48 hours to drill each hole, plus another 11 hours to deploy the cable and DOMs. All DOMs had to be carefully tested before they were deployed, because once they are frozen in the ice, they can no longer be physically accessed. Fortunately, all DOMs are wired to the IceCube lab at the South Pole, so we can still troubleshoot electronic problems and update software remotely. Over 5,000 of the original 5,160 in-ice DOMs are still operational today, even after 10 years. Now the IceCube collaborators are getting ready for the IceCube upgrade, an NSF-funded enhancement of the existing detector. 7 new strings with new and enhanced DOMs will be added to the center of the IceCube array. This more dense portion of the detector will help IceCube collaborators study neutrino oscillations, which is the strange phenomenon of neutrinos changing from one type of neutrino to another as they travel. The upgrade will also help us to better characterize the ice around the IceCube sensors, allowing IceCube to resolve the neutrino sky more sharply. Plus, understanding the ice better will enable IceCube scientists to improve reconstruction of archived data over the past 10 years. It's as if you went to an art museum, but forgot your glasses, and then you come back years later with your glasses, and suddenly you're able to see the art in more clear, vibrant detail than ever before. Construction on the upgrade in Antarctica was supposed to start later this month, but that's all changed because of the COVID-19 pandemic. Antarctica remains the only coronavirus-free continent, so activities at the South Pole, like operating and maintaining the IceCube Observatory, have been able to continue on as usual. But now that the pole is opening back up, the U.S. Antarctic program is taking special precautions to keep COVID-19 out of Antarctica, including limiting the number of people that will deploy this season. IceCube had planned to send a few dozen people to start work on the upgrade this austral summer. Instead, we will only be sending down 2 new winter rovers and bringing our 2 current winter rovers back up north. Speaking of our current winter rovers, it's time to meet them. Dr. John Hardin and Dr. Yuya Makino. They will take you around the South Pole, including the station where they lived and worked for the past 11 months, and of course, the IceCube laboratory itself. Here's John and Yuya.